Hi class, I'm still not feeling super well, so I'm going to do another remote lecture to post for you. Some of the slides that you'll see in these videos I've copied from last year's remote lectures, and some of it I'm filming fresh this morning. So there might be a little discontinuity as we jump from slide to slide. Let me know if any of it is too confusing and you have any questions. Maybe the first thing on your mind is our test on Friday. That is going ahead as scheduled. This slide is showing some of the information that you'll see. So here's the information, kind of the instructions for the test. It's only a single question. You're allowed to have a calculator, but nothing else, no smartwatch, no cell phone, stuff like that. The test, the question, should take you about 12 minutes to finish. I'm going to let you take up to 23 minutes. So hopefully everybody's going to feel like they have enough time. Here's the formulas that you may or may not need. The material covered are going to be lectures 1 and 2 and any associated homework questions that I've made available. I might make it back to campus to Friday, I might not, but the test is still going to go ahead. If I'm not there, then your lab instructor, Mr. Hayden, will be there. The test is pretty straightforward, I think, but if you do have any questions, he'll be well equipped to answer them.
Let's do one more example of a line of charge, but this time let's kind of kick it up a notch. Let's find the electric field at a point P near a long positively charged rod, so that's this one, with a variable charge density, lambda equals A times X. So here A is a constant and X is going to be a variable. So the charge density is not uniform. So where X equals 0, right here at the origin, the charge density is 0. Up here where X is the biggest, here the charge density is the biggest. So this is non-uniform, but we can still do it following our steps from our previous examples. So the first thing we do is we pick some small element of charge on our rod, we color that in and we label it dq. We draw the element of electric field created at point P due to our element of charge, dq. Since it's positive, the electric field will point away from it. So there's our little bit of electric field created by dq. It's a vector, we'll call it dE. Okay, next let's deal with our parameters and dq. First thing I'm going to do is I'm going to label the length of the rod L. And I'm going to say the distance between the end of the rod and the point where we're trying to find the electric field is D. If we write down dE, we know that dE is equal to K times dQ divided by R squared. So let's get R in our diagram. R is the distance from dQ to our point P. So R is from here to here. We also want to get our coordinate system on there. We know Y is vertical. There's not much going on in the vertical direction. X is our horizontal coordinate. So X is going to be the distance between the origin and our point DQ. X will be a variable because the value of X depends on where we drew DQ. If we draw DQ here, X is small. If we draw DQ here, X is big. So X is going to be a variable. Okay, we also want to relate dq to the parameters of the system. So we'll still use our same approach as before. dq is going to be the charge density times the size dimension. So our charge density is lambda. Our size dimension, dq, is a little bit in the x direction. So the length of dq is dx. Remember, when we have a horizontal rod, we use dx, vertical rod, we use dy, arced rod, we use ds. Okay, so we'll fill in that lambda equals a times x times dx. And now we have to put together the fact that we have an x here and an r here. But if we look at our picture, we sort of see that x and r are coupled together. So the distance between the origin and our point P, we can write that two ways. It's length L plus D. So we can see that L plus D. We could also write that distance as x plus r. Okay, so there's two ways to write it. It's either L plus D, that gets us from the origin to P, or it's x plus r. This gives us a relationship between x and r. I'm going to solve my expression for r. r equals L plus D subtract x. Okay, now we want to find the total electric field. So we'll say that the magnitude of the net electric field is the sum of all the little bits of electric field. I'll fill in what dE is, K times dQ over R squared. Next I'll fill in dQ and R. So I've got the integral of K. dQ is A times X times dx. And I'm dividing that by R squared. So that's going to be L plus D minus x, and that has to be squared. Okay, this is an integral that we can deal with, and we'll get to that on the next slide. So our next step in the integral is we'll take our constants outside. E is equal to K and A. Everything else has a variable component, so it's inside the integral symbol. X dx divided by L plus D minus x all squared. We need to put limits on our integral from some initial x to some final x. We integrate over the length of the rod. So let's start at the beginning where x initial equals 0, and let's stop at the end where x final equals 0. So xi equals 0, xf equals L. For the form of our integral, we can look up a result in a textbook, and from a book I can see that the integral of x dx divided by a times x plus b all squared is equal to b divided by a squared times ax plus b plus 1 over a squared natural log of ax plus b. Okay, this fits our problem where a is equal to minus 1 and b is equal to L plus D. So now we can use this result. Oh, I wrote an uppercase, should have been a lowercase. We can use this result to evaluate our integral, and we see that E is equal to K times A. Let's fill in all of our terms here. So we've got B, which is L plus D in the numerator, divided by A squared minus 1 squared times AX, so minus X plus B, which is L plus D. And then we're adding 1 over A squared times the natural log of AX, which is minus X, plus L plus D, and then this all has to be evaluated at L in 0. Let's keep going now. For our first step, we'll recognize that minus 1 squared is just 1, so we don't have to fuss about those. In our next line, we'll fill in our x equals L terms and our x equals 0 terms. So we've got Ka outside of L plus D divided by minus L plus D, so we filled in x equals L there, plus natural log of minus L plus D. Let's put a bracket around this guy. And then we're going to subtract the x equals 0 term, so we've got L plus D divided by 0 over L plus D, 0 plus L plus D, plus natural log of 0 plus L plus D. Okay, so there's our next line. Remember to close our brackets. Let's look at what we've got going on here. Minus L plus L, those guys sum up to be 0. That happens here as well. Over here we've got L plus D on top, L plus D on bottom, so then that whole term is just equal to 1. So let's write that out again, make it look a little nicer. We've got K times A outside of L plus D divided by D plus the natural log of D. I've got an absolute value symbol here. D is positive, so I'm going to drop my absolute value signs. And then I've got subtract. This term is my 1. And then I've also got subtract natural log. Again, I've got absolute values here, but L plus D is a positive term, so I can just drop those and write it as brackets. Okay, I can simplify this just a tiny bit more if I look at this expression. This by itself would be a reasonable enough place to start, but we can simplify a little bit more. L plus D divided by D is the same as L over D plus D over D, which is equal to L over D plus 1. And natural log of D, minus natural log of L plus D. You might remember that the natural log of A minus the natural log of B is equal to natural log of A divided by B. So we can use those two things. So that's equal to the natural log of D over L plus D. So that gives us our final result, that our electric field, the magnitude is K times A times L over D. So we'll have L over D plus 1 here, plus 1 minus 1, that's just 0. Then I'm left with plus the natural log of D over L plus D. That gives me the magnitude of my electric field vector. I do have to write it as a vector. I see that it points right. So for my final answer, my electric field vector is K times A outside of L over D plus the natural log of D divided by L plus D, and it points to the right, so in the I hat direction.